Okay, so welcome to the course in solid-state physics, or condensed matter physics. I never remember what's the official name. And basically this is a very different course than you're used to during your undergraduate studies, because it's not a course that concentrates on a specific theory of physics. It's not mechanics or electromagnetism or statistical mechanics or quantum mechanics. It's trying to understand properties of materials, combining all these subjects. So it's not like quantum mechanics that we have a theory, we study the theory, do some examples, solve some problems, and we know the material. Here, our goal is to explain some of the properties that we see in the material world, or more specific, some properties of materials, using all the knowledge that we have gathered till this point in physics. So we will see different phenomena, explain it in different ways, and the challenge is to understand that not everything is a straightforward progression of a theory and another theory and another class, but it's more trying to understand some properties that we have in materials. Most of them very important for today's technological world. As an example, semiconductors. All of you are probably aware that you're within 50 centimeters of a device that couldn't have existed if we don't understand the properties of semiconductors. And our goal in this series of lectures, in this course, is to gain some understanding, not complete, not all phenomena, but some representative phenomena that are important for these materials. Okay, so basically when we are saying solid state, what do we mean by solid state? Let's try a layman definition of what is a solid state. Please.
The particles are relatively stationary. There is maybe some symmetry that is discrete.
Okay, now you are way forward. When you're saying particles, until 1905 actually, not all physicists agreed that material is composed of particles.
Something that is rigid, that doesn't change its form, and even if it does, it's a very small change. That's linear with force.
Okay, that's already a much better definition of solid state. But in a sense, it's not the type of solid state that we are studying in this course. We are studying a I would call it a subgroup of these types of materials that we intuitively call solids. Now, okay, it doesn't change its shape. That is a very good definition, but when we are saying doesn't change its shape, on what scale? I'm taking a glass of coffee. I won't do it here not to create a mess, and I pour it, and within half a second all its content is on the floor. I'll take such a glass filled with honey. Will take tens of seconds to pour out, but more or less you'll continue to call it a liquid, right? High viscosity, to whomever this term means anything, but still a liquid. Let's look on this thing. What is this?
Yeah.
Is it a solid?
No.
Why not?
Well, it's amorphous.
Well, amorphous is part of the definition, and indeed we won't do amorphous materials in this course. Perhaps as a graduate you'll have a course on amorphous materials, but it's even worse. It flows. Now you can stare at it and you will not understand the statement, but on scales of hundreds of centuries, glass flows. Now there's a huge argument if it's a correct example or not. If you're looking on glass panels in cathedrals in Europe that exist around 1,000 of years, their bottom part is thicker than their upper part. And it's usually contributed to the fact that during this 1,000 years, atoms flowed to the bottom of this glass panel. There's an argument a few years ago, some researchers said, no, it's actually, that's the way that they prepared glass, and when they installed it, they saw a thicker part, so they put it in the bottom. Who knows? I don't know what is the right answer. But on very long scales, glass flows. Now, it even has the scale in which a material that is not solid but looks like solid is actually has a very nice name from biblical origin. It's known as Mispar Devorah. Vorah's number, you can Google it. And why is it connected to the prophet Vorah? Harim nazlu mipnei Hashem, which says that mountains flow before the Almighty. Mountains flow, a flow of something that looks to us as solid. That's why they use this gave that name to this parameter. Okay, so we are dealing with solids, and we have to understand that not all that looks to us as solid is necessarily a solid. Now we can go into some more specific definition, and that already depends on the features that were mentioned here. From what are those materials built? Well, so any material that we are exposed to is built out of atoms. Usually in daily life we are not so much exposed to plasmas or things like that. Plasmas is a situation where the electrons and the nucleus are disassociated, therefore it's a different behavior, but that's common perhaps on the surface of the sun, not so common on Earth or in lower temperatures. Okay, so, and as I mentioned previously, atoms is a new feature in physics, relatively new, 120, 130 years. The first proof that atoms are concrete physical entities, not just concepts or models like Boltzmann used to describe the behavior of gas. Who knows who came up with that?
Thomson, the Golden sheet experiment.
No.
It's the nucleus.
That's a nucleus. That's already a subatomic part.
Dalton?
Dalton found out that there is a specific ratio in all kinds of chemical interactions, but it hinted that you have something discrete there, but not, some people didn't accept that it's atoms.
Brownian motion, Einstein.
Exactly. If you're in doubt, choose Einstein to answer.
1905.
1905 is a famous paper which not only proved that you have atoms, what he did there, looked on a very light particle and saw its motion. And the motion comes because statistical fluctuations in the number of atoms that hit it, and he could even gather from it how many atoms do you have in, let's say, a cubed centimeter or something like that. So, okay, so all materials that we know, gas, liquids, solids, have atoms in them. Okay, now, next step. How do these atoms interact with each other? The simplest case is the noble gases. They don't. That's a simple answer, which is within good approximation, good enough. And basically these guys are the gases that you learned in thermodynamics and things like that. PV equal whatever. And all these rules of ideal gases, these are the gases. Noble gases, they are inert chemically, they don't want to form molecules, they don't want to interact with other atoms. All is good. And gases, ideal gases at least, are in some sense the easiest to understand. So we have there all kinds of macroscopical rules that connect between temperature and pressure and all kinds of things like that. And basically the questions that we like to ask about solid state physics, like what is the electrical conductivity, what are the modes of acoustic waves in them, are either very easy or non-relevant. There's no electric conductivity through an ideal gas. Liquids, there is already interaction. It's not strong enough to fix a structure between these atoms. Actually, liquid is even harder to understand than solid state, and except for some very general behaviors like the Navier-Stokes equations, those of you that did hydrodynamics know that it's not simple mathematics there, are challenging problems. Again, we're not doing here liquids. Solids, you have a structure that is more or less constant in time. And will be even more specific. When we're saying a structure, it could be some structure that is amorphous, has no regularities. Silicon oxide is an example of such structure. What is that? That's the insulators that you have in all your electronic chips. Very important material, but almost no structure, at least if it's very thin on the surface. All other solids, regular solids, have a precise structure of their atomic arrangement, which is known as a lattice. Okay, what we will do during at least the first part of the course is going and seeing what is the mathematical definition and consequences of having such a repetitive structure. What is the influence of it on the vibrations of atoms in a solid? Why are vibrations of atoms in a solid important? First of all, it reminds us of all the behavior of ideal gas. We did thermodynamics on gases. What does it mean? Atoms move in this box, and you increase temperature, you increase their kinetic energy. And from that, you got all that you know about thermodynamics. What happens when you increase the temperature in solids? Well, you have some influences. It expands a bit.
It can also contract.
Certain situations it can contract. The most important thing is that the atoms continue to vibrate, but they stay more or less on average at the same position. So we'll have to build a model that describes it and see what the consequences are. So, after we define what is a lattice, and there's one point in between, how are we convinced that we have lattices in materials? First proof I'll do immediately. Just look. This is a piece of quartz. Quartz is silicon oxide 4 or something like that. And you see that it has a very defined structure just because you see all these facets. It doesn't break randomly, it breaks in very clean atomic thick layers. Another example that if I had something of this size, I wouldn't have to waste my time here, would be a diamond. Unfortunately, it's much rarer and nothing of this size, I think, exists, but please pass it around and try not to drop it. It is expensive, nevertheless, although it's not diamond. Okay, so the fact that when we cleaving is cracking a material in order to remove part of it, that it cleaves in a very ordered and fixed facets, that's perhaps the oldest clue that we have some ordered structure in nature. Those are the crystals. Yes?
Is that the reason why when you break glass it percolates?
Glass is an amorphous material. It's even a liquid, as we said. Because the structure there is not ordered, when you hit it, it doesn't break cleanly, but breaks along different paths depending on the structure, where atoms are closer or further, and you get structure. You know that people make a living out of cleaving diamonds in certain shapes, meaning that if you give, you hit it at a specific angle with a specific force, you can build a very nice symmetric structure, and that's what all the diamonds and other rare gems works on. These give a very nice return of light along the facets. Has a very clear structure, and it's people like it. It's even in the case of diamond, even industrially useful because it's very strong. So we look on this structure and it has properties. Solids, as you can see, may be transparent to light, this thing, or it could be opaque. Why? At the moment, we don't have the tools even to answer it.
But that also depends on the frequency of the light, right? It's not
Right.
like to all frequencies, it's not...
Right, right. And we'll see why. That has to do with quantum mechanics. Quantum mechanics will go into this explanation, why certain materials are opaque and certain materials let light through. Even more, this quartz is actually an insulator. But if I take a metal that I claim has a similar structure, although if you take a piece of metal you don't see it by eye, we'll discuss how am I convinced that that's the behavior of the atoms, the arrangement of the atoms. So if we take a piece of metal, it's a very good electrical conductor. Might even have magnetic properties. From where do they come? Again, quantum mechanics. Without quantum mechanics, we have no tool to answer it. And basically, you can have also interesting optical properties, not just transparent or non-transparent. Here I have a calcite crystal. Calcite is calcium, carbon, few oxygens, I don't remember, 2 or 3. And it shows bifringence. Meaning if you put it on a piece of paper with writing or on your computer screen, you'll see everything doubled. You can try it. So you can get strange optical properties which are not only transparent or opaque, but also some other strange behaviors that are technologically very important. In laser technology, bifringence is a very useful property. Okay, and then we have our good old friend, where all your technology is built upon. It's semiconductor. It's not silicon for some reason, it's germanium. But a close cousin. If you hold it and look on it, it's very similar to a metal. Feels like a metal, it's heavy like a metal, but it's not, it's semiconductor. What is the meaning of semiconductor? Again, in this course, into account that it's heavy. And this is cut. The reason that it's quite expensive, it's cut exactly on a crystal facet. And if anyone wants to know what is done in semiconductor industry, the first part is growing such a thing. Very, very precise in its atomic composition, cut exactly. And nowadays it's not just something of 10 centimeters. They're doing it on a radius of 4 meters or something like that. Yes?
I'm interested if this Quartz is made in the lab or mined somewhere in the world?
I think this is mined.
Yeah.
Quartz is what's known as semi-precious. It's not like you have to break the bank for it, but okay, so lattices. Well, you can still stop me and say, how do I know that solid state materials usually are built out of lattices? X-ray diffraction, and we'll see how it's measured, what is the theory behind it, what does it teach us. But at the moment, we'll just, at the beginning, we'll do just a mathematical definition of what is a lattice.
Yeah, Richard, will we learn about the renormalization? Will we learn about the renormalization?
Renormalization group? No. That's graduate. Gavish. Or Sarig. It was asked how it's said in Hebrew, so... גביש זה השם הכללי שנתנו, זה התרגום אולי יותר מדויק של קריסטל. לטיס ושריג. Okay, so a definition of a lattice. I'll give two definitions. One sounds very general. The second one is very conductive for mathematical proofs and checking if something is a lattice. So the first definition an infinite number of points, and you can stop me here, no material is infinite, right? So for the purist you don't have a lattice in nature, because it's always finite. Usually if it's big enough, the effects of the boundaries are less important, although sometimes they're extremely important. Again, I'm going back to your electronic devices. Almost all the properties that are used to build memories, CPUs, and so on, comes from the boundary between two materials. And hopefully at the end of the course you'll understand why. Okay, so it's an infinite number of points. that if I'm sitting on a point and looking around, I see the same environment. I see exactly the same structure of points. I'll give you an example. And lattices could exist in 1, 2, 3, any dimension. Of course, in solid-state physics, we will usually think about three-dimensional structures because we happen to live in a three-dimensional universe, and if anyone here has an idea, he can phone up Sweden and ask for a Nobel. But that's what we see around us. But one can think on 1, 2, and any number of dimensions. So I'll start with the easiest case for me to draw. It's a one-dimensional lattice. And continues to the left and the right to infinity. And assuming that I have the same distance a between all these points, if I'm sitting here and looking to the left and looking to the right, I see points at distance a, then at distance 2a, then at distance 3a, and so on and so forth, which is exactly the same that I see from this point. Yes?
If the distances are A, B, A, B, A, B, A, B, so it's not exactly seeing the exact thing from any point, because is it okay?
Wait with this question 10 or 15 minutes. The simple answer, no, it's not a lattice. The more complicated answer, yes, but you have to change the definition of what's a point of the lattice.
2 points and then
Combine it to 2 points, and then you'll see exactly the same. But the situations that you have referred to, let's say, where the different colors are points A of type A or B, or atoms of type A and B. If you're sitting here, your nearest neighbors are black. If you sit here, they're purple. So not all points is the same. No, it's not a lattice by the definition that we gave.
Can we say in that case that the lattice is something that we can find in an order in which there is translational symmetry?
Yes, but wait a minute. That's the next step. In the definitions that I gave, I wanted to be well understood that this is not a lattice. Okay, I can do it also on 2 dimensions. Is this a lattice?
Yes.
Assuming that it continues to infinity? Yes, definitely. Let's say that A is B. You have 2 different distances.
still.
Is this a lattice?
Yes.
Let's have a vote. Yes? No? Democracy works. The majority voted that it's yes, so no, that's not the reason. Just
Also in the test we can just vote what is the
Well, in some interpretation of postmodernist science, you could, unfortunately, this class is not run by these principles. Still believes there is some kind of truth. Why is it? Because each point you see to your left and to your right, neighbor at distance A, and up and down, neighbor at distance B. Okay, I didn't say that in all directions you see the same thing. I said from each point you see the same environment, and this certainly is a lattice. This is not. And as a last example, this is known as a honeycomb lattice. Is it a lattice?
No.
No. Although it's called a honeycomb lattice, it's not a lattice.
Like, it's not how it's the honeycomb, because it's I have like a
You have, that's just to aid your...
אבל יש לך מאויג בהם, זה לא רק מישהו ש...
Okay, so maybe I did a mistake here in drawing it.
תיצור את זה דרכה ואז תכניס שמות מששב זה
Okay.
I'm sure it should be a lattice. There should be a way.
You made the corners touching. That
Yeah,
is the,
you need the edges
two
touching, not the
to the
corners.
left. They shouldn't be touching the two.
Right. Okay, anyway,
This is two, not a lattice.
hmm?
This is not a lattice.
This is not a lattice either for the simple reason that this guy... Well, actually the easiest way to do it is to actually draw a triangle lattice, which is a lattice, and eliminate some of the points. Okay, so that was one definition that encompasses all the properties, but is not, well, it's precise, but it's not very comfortable for mathematical manipulations. The second definition is well, the number here in 1 and 2 and 3 depends on dimensionality. For a one dimension, you have just 1. For 2 dimensions, 2. For 3, 3. For n, large n dimensions, you have n. Okay, so let's see it in the examples that I gave, and I'll try. Okay. This guy, first guy. So, if I call this the x-axis, and I choose n, well, I forgot here to put n1 and 2 and 3 are just integer numbers, 0 plus minus 1 plus minus 2, so on and so forth. All the points are described by these constant jumps between them. Okay, self-evident. Well, in this language, here I can define two sublattices. If I'll write down that would be a lattice for the either black or purple points. Because jump to n each time, you'll see you'll land on parts of a lattice, on points on the lattice. For this guy, this will be the lattice vector of this
Which one?
it's for all points. Choose n1 and n2 and it will be on a specific point. The vector is a structure. n1 and n2 could be any integer number, positive, negative, 0, whatever. Do they have to be the two parts orthogonal? The answer is no, definitely no. Let's say, for example, let's try to get this one correct. So I have here constant distance A. I still have here constant distance. Okay. So as I have paralleloids between these okay. Is that a lattice? Yes, it's definitely a lattice. So how do I write? We'll have let's call this guy alpha. Could be anything. Would be 90, so we're back to In general, I could write a set of A1 These are my the components of the vector so far. Same I can have with 3 dimensionals and so on. Okay, using these 2 definitions, I can build a whole zoo of different possible lattices. Let's start for our 3-dimensional, I'll just give a few examples. The simplest 3-dimensional structure that we have is simple cubic. Which corresponds to its name. And a lot of times, instead of just writing the explicit form, I'm just writing that I defined a simple cubic lattice. Unfortunately, almost doesn't exist in nature. Very nice for homework assignments, not very relevant for what appears in nature. Why? A good question. There are 2 cousin structures which are very ubiquitous in nature. Why? I'll give you perhaps it's a good question. I'll give you a semi-intuitive answer, but which holds a lot of truth in it. Let's say you have balls, spheres, that you want to pack. How will you pack it? One on top of the other? Would be very unstable. How will you pack it? You'll pack, let's say, 1 layer of balls touching each other. The second layer you'll put in between them, right? These are exactly the 2 cousin structures that exist. Well, it sounds as a good explanation, but there is one small problem. There is such structures as I described, but not exactly a lattice which is table salt. Na and calcium appear on one on top of the other, but they are 2 chlor. are one on top of the other. מלח שולחן. They are very close to simple cubic, but it's two different kinds of atoms, so it's not a lattice, at least for now. Okay, so the two cousin structures are and this is the last time you'll see the whole name because usually it's referred to as BCC, where the structure, and I write down the three vectors, well, the first two very similar. That's what I told you, a layer that I put down in a cubic structure. And this is a point exactly in the middle between them. And this guy has quite a lot of examples. One of the best known materials, iron. And quoting correctly, for iron A is equal 2.57. Holy. Okay. Actually, the order that I have written, it has no meaning at all. I could scramble it, it doesn't permutate it, it doesn't make any difference. And here basically you have an atom in the middle of each cubic face. This is a very ubiquitous structure. Aluminium, gold, copper, a lot of metals have this structure. Yes?
Yeah, two things. One, what about chalk? Give.
Excuse me?
What about the chalk? Give. Does that material has
A
that
structure?
kind of symmetry?
Good question. Google it.
But about the last equation that you wrote, wouldn't it be easier to transform these coordinates such that the center of each cube is between the material, that the vertices are the...
At the moment, we define the lattice just with a set of points, and you have to define the lattice vector as going to these points. Okay? Now, in a moment, well, quarter of an hour, we'll already try to have a more abstract definition, which we will call a basis, and we'll see what that is. More questions? Yeah.
Can you draw the difference between the two of them?
No, but you can Google the difference, because if I'll try to draw it on a three-dimensional plot, you won't understand anything, and just coming here and putting you a slide. No, I prefer you to go after the lecture, and there's wonderful pictures of all these lattices. In the internet you can find and see and get rotated and see each structure, and you get a much better feeling from me showing you a slide of it, and then you don't go and play with it. Yeah.
Can we build specific shapes in the lab, like specific formulas?
The answer is yes and no. What do I mean? It's a good question. At the moment, if you want to build something on an atomic scale, you don't have full freedom to put any shapes that you want. Why? Because there is chemistry between atoms, and if you're trying to push, let's say, two atoms at a smaller distance or at a larger distance, it won't be stable and your lattice will fall apart. Now, you do have the ability to build structures which are larger, on sizes that are microns and even tenths of a micron, where you have building blocks that repeat themselves. Now, I don't know how many of you have heard about something called metamaterials. These are exactly materials that are built out of building blocks that are ordered as a lattice, and they have very interesting optical and electrical properties. And they are used all the time. For example, you can build structures that are either transparent or totally reflective for some wavelengths of the electric material, of the electric wave sent to them. Okay, what else can I tell about the material? Well, I have a property that's called coordination number, which is simply the number of the nearest neighbors. Okay, what is the coordination number of simple cubic? 6. I have 6 closest atoms to any point there. Okay, what's your guess? Will it be larger than 6 or smaller?
Larger.
4.
Nine.
Or it's 8.
It's going to be 8 because at the center of the cube, it's
Right.
going to be 8.
Because you have an atom at the center, and look on the layer above it and below it. Those are the 8 corners of the cube. So it's 8.
All of them are with different distances.
No, exactly the same. Think about 2 layers that, and then you have a layer in between that is shifted. If you're looking from a point in the shifted layer, you'll have 8. You're not convinced? Again, take a drawing of a BCC, rotate it and see it. Even harder to count, but that's the number. So this actually has importance on some electronic properties of the material, the number of nearest neighbors. We don't know yet what, but it plays a role. Okay, let's look on some example. The definition is very simple. Any cell with which I can tile all the space. For example, if I'm looking here on a lattice, it's not a square lattice in this case because A is not equal B. I can build, say, such a block, and assuming that I actually do a lattice that covers all space. But I could have chosen something else. I could have decided I want to draw like this. Again, it's okay. It's not uniquely defined. you want one property of a lattice is that you can tile all space with one shape. Okay? If I have a lattice, I can use one tile to cover all space. So in this case, any square-like structures that I'll take, I can use to tile the space. So that's known as a unit cell or a primitive unit cell. The meaning of primitive is not developed, but basic. So it's a basic shape with which I can tile all space. Look on the tiles on the floor. It's an example of such tiling. Once upon a time, it was believed that only lattices can be tiled with one shape. Penrose is the first that showed that with two different tiles you can actually tile the whole space, even that it's not repetitive. And actually a year ago, someone came up with some strange hat structure that also can tile in a non-repetitive way all space. But okay, so primitive unit cell is not unique. As you saw, I can put the shape here or wherever I feel like. Wigner Zeitz, to physicists, Wigner, you probably heard this name before, is a type of a primitive cell which we have an algorithm how to build it. And the algorithm is very simple. I'll draw here a square lattice. First, draw a vector to all nearest neighbors. In this case, z is equal 4 for two-dimensional on a simple cubic. Okay, so I go okay. Then define a point on the vector that is the middle between those two points. 1, 2, 3, 4. Then draw a perpendicular line. And you got here a primitive unit cell, but a specific one, right? By construction, I got a specific one.
Does it have some special properties that different than normal?
Well, first of all, it helps you to translate your statements. If I say I want to discuss a Wigner Zeitz cell, I know exactly on what I'm talking about. when I'm saying a primitive unit cell, could be anything. It will become more important when we'll define Fourier transforms of these lattices. And why are we going to a Fourier transform? Don't worry, it's not in this lecture, it's the next one. Because we'll talk about waves passing through a lattice, and every time that we talk about waves, Fourier transform becomes important. Okay. Now to the question that was raised about an hour ago. What happens with a repetitive structure that doesn't fulfill the conditions that I gave? The simplest one So this is not a lattice. But we clearly see that we have here a structure that repeats itself. So then I construct a lattice that's known will have an additional A there. Some. Could someone
revise? It's not revise.
IES, right?
Right.
Why didn't French monks learn to spell in a normal way? Unclear. Okay, brevet. What do I do there? I replace my two different points by one point. Where do I stick it? Wherever I feel like, as long as I'm consistent. So I can take this structure, replace it with a point at the same position, and the basic lattice is not a lattice, but this construction, this X, is a Brevet lattice. And this happens a lot. Table salt. We have there two different atoms. But if you contract them to one point, it's a well-behaved lattice. Diamond is not a lattice. Structure of a diamond is not a lattice, but if you take create out of each two atoms a point, this is an FCC lattice. So we'll see it has influence on all kinds of behaviors of the lattice, but it's still a lattice. We can refer to it as a lattice. Questions? Yes? Exactly. Now, let me start actually from okay, this is a triangle lattice. Each point, how many nearest neighbors do I have?
6.
6. So a regular lattice, don't need to correct anything. Now let's see if I'm able to build out of it.
You have to quit the center ones, right?
Right, but I have to pay attention. I take these off and I have the same problem that I had before.
The second, the forehand in the last.
No, if I take here, I'm back with my. These don't belong. You know what? To make life simple, I'll keep it on 2. So, if I'm taking these, okay, now I know what.
I think you need to take every other point from every
Yeah,
other point.
now I have it. Okay. Okay, 2, 2. So on. Okay, this is the honeycomb lattice. Okay, you see, if it would have been the same distances. Okay, if I have drawn the distances correctly, a good honeycomb lattice. What's wrong? Why it's not a lattice? Look, this guy has 2 to the left and 1 to the right nearest neighbors. And this guy has 2 to the right and 1 to the left. Not the same, not a lattice. But if I take it and let's say connect these and turn it into a brevet. I have a well-defined lattice. Each point is the same. 2 neighbors up and down and 3 neighbors, sorry, 4 neighbors left, right, and so on. Well, it's actually a triangle lattice. Did I have to choose this pairing? No. Could have chosen, let's say, give me another shape. Here and here and here and here and
Let's also choose like the one above one, like 2 points that are one above the other.
whatever I can. No, I think I did it correctly. This guy is connected to a guy up here. That's fine. I cover all of them. It's also a brevet lattice. I chose different combinations, but okay, I'm entitled to do it. So the honeycomb lattice, which is not a lattice, becomes a Bravais lattice if I built a structure of 2 atoms and replace it by 1 point. Additional questions?
Can you put a node in the center of the hexagon and use that to equivalent to the 6?
Now, a bit more complicated structure, and we'll talk in the next. I could take 1/3 from each point here and put a point here instead of it. Yes, that's also a Bravais lattice. It's for my discretion to decide how to do it, as long as I keep one rule and do it everywhere. Yes?
So the total sum of the particles will be כאילו שיהיה לך 2 ל-1, כאילו שיהיה יחס זה, או שכאילו אם היא לוקחת משושה ועושה מדברת את זה לא משושה, כי אז יהיה צפייה חמה.
When I'm building out of a hexagon, my main point, my 1 point, you have to take into account that they are also taking, let's say this point is 3 times. So it's 1/3. So it's 1/3 times 6. 2 points are actually building this point, and that's a basic property of this Bravais lattice. I need 2 atoms, doesn't matter how I compose it, to turn into 1 point. If I'm taking 2 and turning this way, or 2 this way, or 1/3 of 6 and sticking it here. Yeah.
Since I'm turning the 2 into 1 point, can I decide that I turn 2 into 1 point, then the adjacent one I take only 1 point and build it that way?
No, because then it's not a lattice. One of them is built out of 2, one is built out of 1, so they're not the same. Lattice, the basic definition remains. All points look the same. Yeah.
If I got 2 lattices like this, is there a way to, I don't know, combine 2 or like?
Yes, you can also build 2 lattices and put them one on top of the other. But then it's basically a Bravais lattice. It's the same. Because then you can take a unit cell of 2 atoms, turn it into 1 point. That's that. Okay, so just a few words about the general structure of the course. If I'm not mistaken, it's 80% exam and 20% homework. So please do homework. I can't emphasize how many times people who were on the verge of passing the course just failed because they didn't give in their homework at time. Second thing, since everything here is recorded, some people will think, okay, I don't have to appear in the lecture. I can just, at the end of the course, sit down for 3 days, see 40 hours of video and know everything. Guys, it doesn't work. Just experience. Last semester I had a course in quantum mechanics, and it's amazing how well this predictor worked. There were 13, 14 people who appeared more or less for every lecture. None of them received less than 85 in the exam. There were 25 or so that didn't appear or appeared for 1 and 2 lectures. 2 or 3 of them got above 85. Well, that's a scientific fact. Why is it? I'm not sure that it has anything to do with being physically in a class or seeing recording, but it has a lot to do with the fact that human mind can't accumulate a huge amount of knowledge and internalize it and really understand it in a short time. So if you listen to the recordings each week, I don't know if there's a big difference of you sitting here or sitting at home, but experience teaches us that if you're not here, you don't listen to the recordings, you get to a few days before the exam, you sit down and listen to 40 hours of video, everything is a whole mess in your head, you're coming to the exam and everything looks like a foreign language to you. So, my recommendation, I'm taking into account the fact that if you're in class, you can interact, you can say, I don't understand, you can sit down for a moment and think on the questions asked by your friends discussed in class, try to come. Of course, if you have some special circumstances, I can't say anything, but for your own good, appear in class. Okay, so we'll stop here.
Thank you very much.
Guys, the conceit. תגיד לי אתה. Hey, the conceit latin.
אני חושב רק משהו